All right, so ratios and proportions. First of all, who remembers anything to do with ratios and proportions? Nobody? Okay. So this is all about comparing numbers. So this we innately do all the time. Think about anytime you go grocery shopping or shopping in general. What do you do whenever you go shopping? How many of y'all price check everything and try and find better deals and things like that?
Always.
Exactly. Everybody always does that on everything you buy. You don't sit there and just say, oh, here's this, I'm going to get it no matter what. I don't think there's a person out there that does not price shop. Whether it's a car, new clothes, groceries, what have you, all of us innately want the best deal. I can give you for an example. I was at the store the other day and I saw two different boxes of cereal. One's called the family size, one is the giant size. The giant size was $1 more than the family size, but it only had 2 ounces more of cereal. So thus, when you start comparing that, the better bargain was the family size. Does that make sense? And this is something we do instinctively, just because we don't like to spend resources if we don't have to. So we compare prices a lot. We can compare baseball, football stats, and scores. I don't know how many of y'all are into fantasy football. I've never really understood it. But whenever you do fantasy football, supposedly what the main thing you're doing is trying to compare stats to build your best team. Yeah? So I think then that's supposed to be it in a nutshell is so and so's got the best this is the best running back, this is the best quarterback, uh, things like that. So we need to be able to express to other people what we're comparing. Um, so we either do this by subtracting or dividing so that we can say, hey, this is this. So yes, we do this all the time. Like I said, just going to any store, you start looking for anything, and all of a sudden you start asking yourself, is this the best price? Could I get this for a lower price elsewhere? Do I really want to spend my money on this? That kind of thing. So think about just driving, okay? When we're driving, what do? We do the same thing. We sit there and say, oh, well, if I take 459, it'll have this much time on my journey. If I take 2059, it'll have this much time on my journey. Do I take a back road? Is that going to be clear at this time of day or what? We innately do this. Some of us become more obsessive compulsive about it than others. Um, Whenever I first moved out to where I'm at and figured out all the different ways I could get home, I started actually timing myself to find the best route and how fast I could go on those. So yes, even I'm guilty of doing this quite a bit. So this is what we mean by this, is that we're taking these ratios of, well, if I go down road A, it takes me 10 minutes. If I go down road B, it takes me 10 and a half minutes. So more than likely, I'm going to go down road A. Just like if you're standing in that grocery store and looking at two steaks. On one package, it says $2 a pound. On the other one, it's saying $5 a pound. What's the weight on? We start asking ourselves, okay, so which one's got the better weight? Which one's the better quality? The other thing we ask ourselves is, what are we going to do with it? How are we going to cook it? Am I going to throw it on a grill? Am I throwing it into a pan? What have you? So we do this all the time in our own heads. We just don't know what we generally call it. But what we're seeing is ratios. What we're doing is making these comparisons so that we sleep better at night. I guess is the best way to say that. Okay. So in ratios, the way the problem is worded is always important. I don't know how many of you have your books yet. So let's kind of talk through some ratios I've got in the book here, just so that you can have some examples of this. So, all right, so the very first one let's look at, and that is got several pieces to it. And we have a machine that produces 2,000 parts. Out of these, 400 parts are defective. So very first question they ask is, what is the ratio of defective parts to total parts? I'm sorry, my writing with this mouse is so crummy, guys. So what is my ratio of defective parts to my total parts? Anybody want to take a guess? So there's a couple of different ways we can. 20%? I believe that's correct. So we start off with 400 over 2,000, but I'll go ahead and just start at 4 over 20 and drop some zeros off this. Reduce that further, and you get what? You get 1/5, right? So it is 20%. Okay, so what if I said, what is the ratio of defective parts to my acceptable parts? What is my ratio of defective parts to my acceptable, my non-defective parts? Well, for that, we're going to have to do a little what? So my defective parts, once again, so we have 4. We end up with 400 over what should be 1600, but I'm going to go ahead and just drop off the zeros. We'll say 4 over 16, which,
No, 1 over 4.
or 1 over 4. If I was to express these in a decimal format, then I would put this as 20% and 25%. Ratios technically have no units. Okay. Ratios essentially have no units, guys. But all depends on how you're comparing these. So in this very first one, we're comparing, what is my total product out of my total production, what am I losing? I'm losing 1/5 of my product in production. That sounds like I need to get somebody in maintenance and kick them in the behind so I can get them working on how to correct this. Yes?
Yes, ma'am.
Because 1/5 of my product is heading out the door to bad places, or I'm having to do rework on them. Not something I generally want to do. Takes a lot of time, takes money, takes effort. And all three of those are no good for business. Okay? However, if I switch that up and instead of looking at my total parts, I look at my acceptable parts, that doesn't give me a good ratio either. So there really is no good way about telling your boss, we got to get some things taken care of. Okay. So we're comparing one number to another, and they can be written in a couple different ways. So you have your fraction, 2 to 5. You have very simplified version of 1 to 2.5. You have your decimal equivalent of 0.4, and you have your percentage. So technically, they've got 5 different ways they've put it on here, but they're very similar to each other. Okay. So the way you express this to somebody can make a very big difference in how they perceive what you're doing. Yeah, I don't know how many of you've got the book yet and can turn to table 3-2. Well, let's kind of talk through this. So if I say the number of defective parts has decreased by 75%, okay, so the way you would express this to your boss is that, or what your boss is supposed to think is that we have 20 defective parts out of every 100. It's decreased by 75%. So now I'm down to only 5 parts per every 100 that are defective. Does that make sense? Okay. So then if you tell your supervisor, the number of defective parts has dropped to 1/4 of what it was. So your supervisor might understand that, so we're down from 20% defective to 5% defective. At least that's what you're hoping to try and convey to him or her. We've cut the defect rates by 3/4. See, now you're starting to get into stuff that you sit there and go, what are you talking about? because most people don't want to do that kind of math in their head. Most of the time, your supervisor sends you out on that call. They're going to sit there and say, okay, go here, take care of this, and then when you get back, tell me what you had to do. And they are not looking for ratios and proportions most of the time, but what they're going to look for is, okay, so did you fix the problem? Is it better than what it was? If you're having to do analysis, that's where this is going to have to come in. So you can go up to your boss and tell them, hey, our production is up X amount of percentage. Does that make sense? Am I sending everybody to sleep at this point? Okay. So let's kind of talk about this particular problem, which is a very interesting one. So suppose it takes 10 pounds of water to produce 4 pounds of product. What is the ratio of water used to product produced? So if we're doing a ratio of water to product, so it takes 10 pounds of water for 4 pounds of product. Yes? So then if you simplify that down to 5/2 or 2.5, so it takes 2.5 pounds to make 1 pound of water. I'm sorry, 1 pound of products. Okay. So what if I said instead, how much water do you use in the processing of each 10-pound container for product sales? That's where you get the water to product ratio. So you have 10 pounds. You would multiply it by 2.5. You'd have 20 pounds of. Okay, so the way they also did this is this. So if you water used in processing a 10-pound container of product. So there's asking how much water is equal to the product times that 2.5, which is the water divided by product. So to replace this, my ratio for this was 2.5. And I'm multiplying it by 10 pounds because that's how much product I'm trying to achieve. So in order to get 10 pounds of product, I need 25 pounds of water. Does everybody kind of get that? Any questions? Go ahead, Mr. Clark. You have a question? You have a question, Mr. Clark? No? All right. So let's work let's work one here. So there are 18 students in a class. On the first quiz, 5 make an A, 3 make a B, 7 make a C, and 2 make a D, and only 1 student makes an F. So the first question is, what is the ratio of A's to tests taken? So first of all, what's the information we need here?
We need to know how many students they made A and how many students we have on the total.
How many A's do I have versus how many students are in the class? So looking back at my word problem here, I have 18 students in the class, so there'll be 18 tests taken. And how many A's did they make?
5.
They made 5 A's. Now then, can I reduce this any further?
No.
No, but I can put that in decimal format. So I would take my 5 and divide it by 18 to get my percentage of roughly 28%. And that's just rounding up, so. So what is the ratios of A's to B's? So again, what 2 pieces? We need to go through our word problem and find the pieces we need. So we know from the previous problem we had 5 students that had A's. How many students had B's? We had 3.
3.
So we have a 5 to 3 ratio. Again, you can't really split that any further, but you can simplify it. You get 1 2/3. Or 1.67. I'm sorry. Yeah, 1.67. So we end up with 5/3, which is equal to 1 2/3, 1.67, or 167%. So more people made A's than B's. 167%. So what is the ratio of F in the class? That one should be kind of easy for you.
Uh, 1/18.
1/18. I know you can't really see this very well because somehow it got flipped. I don't know how that happened. So what you should have had was 0.0556. I'm sorry, 6,550 or 65.5%. So what is the ratio of passing to failing? Now this is not the loss in pass fail. This is strictly like if this was a high school, what's the pass fail rate?
I guess it's A, number of A plus number of B plus number of C plus number of. Oh, yeah. Is D passing? No.
D is technically passing in school, most school systems. It's just not in college.
Yeah, like somebody mentioned in text message. Yeah, it's that one. what's it almost like 17 over 18?
It is 17 over 18. So if you go by the loss since pass fail, that instead changes to 3 over 15 or 20%. Personally, I like this one better because the fail pass rate, so you have one person that failed, 17 that passed. That's a 5.88 fail rate. That's not bad. Lawson State fail pass is a 20%. That's not so good. Okay. So let's talk about a few more. I'm going to put a whiteboard up for just a minute. So if I have so going back to how we do ratios in our own heads every day, if I have chicken that is costing me a total of $8 for 12 pounds of chicken, how much am I paying per pound? So I have,
Sorry, please, one more time, please.
I have $8 for 12 pounds. And I'm looking for price per pound. All right, I'm looking for price per pound.
8 divided by 12.
So you do 8 divided by 12, which would give you what? .67 per pound, or 67 cents per pound. I think we're all having technical difficulties with our microphones today. I had to dial in through my cell phone, so hope y'all are patient with me on this. Okay, so let's look at if I have a slope of 4 inches in 1 foot. Now, before you solve this, what do you need to probably do? Should we compare apples to oranges, or should we instead shift one to the other? So 1 foot would have to equal 12 inches. So it'd end up with 4 over 12, which is also 1/3. Now, I hear y'all kind of thinking, well, what do you care about slopes? Well, two different things here, guys. One, if the slope of your roof, the pitch of the roof, I don't know if y'all know what I mean, but a roof pitch is, this is your roof, this is the slope of your roof. Too shallow and water pools. Too steep, it just doesn't work as well. Okay. So yes, Mr. Clark. Like I said, if nothing else, guys, type in the chat because, like I said, apparently everybody's having trouble with their microphones today. But this slope right here, if you don't get the right kind of shingles to put on it, it tends to cause a lot of problems with your roof. You end up with leaks. Okay, so let's look at another one. So a mechanical advantage of 2 tons lifted by 50 pounds. So what do I need to do for first of all with this? Convert tons to pounds. How many pounds are in a ton? It's 2,000 pounds to a ton, so this would actually be 4,000 pounds, right? So my ratio would end up being 50 over 4,000. You drop off a 0 on each, that's 5 over 400. Divide that out, you should get what? One-eighth. I can lift 4,000 pounds with 1/8 its weight. Of course, if you put it the other way around, I'm having to lift 50 pounds with 4,000 pounds. That's a totally different monster. So you'd end up with 400 divided by 5. Or in order to lift 1 pound, you would need 80 pounds. That's kind of ridiculous, right? But that would be along the laws of, I don't know if y'all remember from science class, the laws of levers. Y'all want to do one more?
I guess.
All right. So if I have a pickup rate of 6 tons in 4 days, how much product am I moving per day?
Three over two.
So you start off with 3 over 2, because once you simplify these both down, that's what you're going to end up with. My decimal equivalent would be 1/2. I'm sorry, 1.5, not 1.2. Jeez. For some reason I thought, anyway. So you end up with 3 over 2, or 1.5 tons per day. Any questions on that, guys? Like I said, this is the kind of stuff we do all day, every day in our heads, especially anytime we comparison shop. Okay. So back to our PowerPoint. So an average is a summary of unequal numbers. Okay, so it's one of those things of, well, let's talk football. What's his average run? You know, if we're talking, who's the current Alabama running back? Can't remember his name now.
Najee Harris.
Yeah, Najee Harris. Didn't he supposedly break a record last game? Or somebody broke a record last game. But so this is what we innately do. We want to break these numbers into things that we can understand. Well, you know, so-and-so has an average of running 20-yard touchdowns, and that's something that we as fans, or y'all as fans, tend to look at them. Not a giant sports fan, so I can't really claim it. So this one they give you is bowling. I don't know how many of y'all bowl. It can be kind of fun. So he got better over the night. So first one he did was okay. So the receiver broke the record. Okay. I said still. I just kind of halfway listened to any of that. So if we start looking at Patrick's bowling record, he got better as the night went on. So he starts off bowling at 180, just better than anything I've ever bowled. Then he got 10 more points the next round and bowled a 190. And then he must have had some real good luck because he bowled a 250. So we're averaging his scores for the night, so we're going to add them up and divide them by the number of times he bowled. So when you add 180 to 190 to 250, you get 620 divided by 3 gives you 206.67 as his average score. Does that make sense, guys? Are there any questions about that? Okay, so if you calculate your grades, so the way grades are calculated, most teachers tend to run this way. Is that you take the number of points achieved and divide it by the total number of points. So you calculate your score by dividing 75 by 95, which gives you 0.789, which generally will get rounded to a 79. Okay. Any questions on that, guys? Fairly straightforward. If you're trying to average your grade, now this is not how we do our grades, because our grades are what? The grades in this class and most of our other ones are weighted. So let's say you make, so on your homework, you might make a 90, on a test, you might make 100. So you would think that trying to average those together would give you your grade, but that's not right because homework is weighted, I believe, at 13%. somewhere in there. And tests are we take the two highest test scores and average those out. So this is kind of why I'm not an overly big fan of this particular problem, but if for a lot of classes, if you have a 95, a 78, 85, and a 90, this is how your grade would average out to an 87. Does that make sense? Okay. So lastly, let's talk about proportions. Again, this is something we kind of do all the time anyway. So this is a mathematical statement that two ratios are equal. The product of the means is equal to the product of extremes. That should sound rather familiar. I'm trying to remember which grade that would have been learned in. I think 6th. But in any case, anytime you do proportions, you can call it extremes or you can call it the outside. Versus the inside. So you multiply your two outsides by, and then you divide by your insides. So for this one, it's asking you if I have 60,000 pounds of product that is able to be made in 16 hours, that should equal 3,750 pounds per 1 hour. So multiplying 3,750 by 16 and then dividing by 60,000 should give you that they are both equal. Does that make sense? Make sense to everybody?
Yes, ma'am.
Okay. So if you only have 3 variables, calculating the missing one is actually fairly easy. You make sure that both sides of the equation are the same. So a car traveling at 125 miles in 3 hours, I'm sorry, a car is able to travel 125 miles in 3 hours. If it traveled for 5 hours, how long would it go? So when you write any kind of proportion, you need to write them the same way. So if you notice, this is miles, this is miles. Change something real quick. This is hours, this is hours. You don't sit there and say, well, this is miles, and this is hours, and that's going to equal hours and miles. No. What you want to do instead is miles to miles, hours to hours. Same format every time. Does that make sense to everybody? Because this is the part where most people have issues with proportions. And the truth is, you actually do proportions a lot in your everyday life. Think about it this way. I don't know how many of you cook or bake, but you probably did as a kid. So if you took, let's say, 2 boxes of cookie mix, you automatically knew you had to double your recipe, right? Or if you cook today and you say, well, if I only need 1 cup of cheese per, we'll say it's a casserole, then if I make triple the casserole, I need triple the cheese. right? That's a proportion. Does that make sense to everybody?
Yes.
Okay. So you automatically do this anyway. So whenever you're looking at this, well, if I go 125 miles and multiply that by 5 hours, I'll end up with the variable x there. So I'd end up with 3x is equal to 625. Divide both sides by 3 to get rid of the 3 on one side. You get x is equal to 208 1/3. Any questions on that?
No, ma'am.
Okay. So let's try, I don't know why these two slides are on here, but let's try a couple of these problems real quick. So if I give you, blank is to 3, that's equal to 3 to 2. So what is my missing variable? What's the first thing I would need to do? I'm going to do means and extremes, right? Outside to outside, inside to inside. So I would end up with 2x, because that's always what we do as a variable, equals 9. Good Lord. Two x equals 9. Does everybody see that? So then you divide both sides by 2. So x would equal 4.5. Did everybody see how I did that? Everybody kind of follow along and know what I did?
Yes.
Okay. So then let me give y'all one of your own and we'll see what everybody comes up with. So let's do, so if I have 100, it would probably be easier if I actually, so if I have 100 is to 30, that will equal x to 9. I'll clean that up while y'all work on that. We won't really be using a lot of pi. Okay, so one of the questions in the chat is explaining the pi factor 3.14. I'm not quite sure what you mean by explain that. We won't really be using that in this class, so I'm not quite sure what you mean by that either. Okay. So I'll give y'all just a minute to solve that, and then we'll go over it. All right, so what's the answer to x?
30.
X is equal to 30. So the way you would have found that was 100 times 9, which would have given you 900. And you would have ended up with 30x, so you just do 900 divided by 30, and it should have given you 30. All right, so one more, and this one could be kind of fun. So 33 and 1/3 to 78. That's why I hate trying to draw on these slides. Always misinterprets. 78 equals 4.5 to x. So this will be the last one, and then I'll answer any questions y'all have. All right, so that should be your answer right there, is that x is equal to 10.53. The whole reason I left the 133 and the 33 and 1/3 as a third is simply because whenever you start moving thirds into anything, what always happens is you end up with 0.3s or 0.6s repeating. And so in order to not have to deal with that, you just leave it as a fraction and you solve from there. Does that make sense?
Yes, ma'am.
Okay. Did everybody get 10.53 or anybody get something different and don't know how they got it? This one is always generally a tough one. Okay, then we will leave it there for the time.